Let's talk about the test. It's 40 questions long, all multiple choice, like the midterm. There will be 2 extra credit questions. So, and those questions I will make a little tougher than the rest of the exam. So basically there's 42 total questions, but it'll be graded out of 40. You get 2 pages, so that's 4 total sides. So you get 2 pages of cheat sheet for the final. I do that simply so you can just reuse the one from the midterm and then make a new one on the chapters 6, 7, and 8. Same rules apply for the final. Bring a calculator, bring a pencil. I will bring the Scantron, so you need to use pencil. I think that's it. Any questions you have about the exam itself? It is cumulative, chapters 1 through 8, yes. Yes. Yes, I do suggest studying up the midterm. I've posted solutions to it online. The chapter 1 through 5 stuff on the final is going to be exactly, same concept, different numbers, but that's really all I'm going to do, change the numbers to make it a new question. But it's the same material that'll be half the final. So definitely go study your midterm. You'll get the full 3 hours like last time. Again, you shouldn't need it. Yes?
And then also, would you say that it's evenly distributed throughout?
No. I would say it's probably half old stuff, half new stuff. Which the old stuff is 5 chapters worth. The new stuff is 3 chapters.
The chapters 1 through 5, 6 and 8, 6 through 8,
Yeah. Which means more from 6 through 8 individually than of any of the first 5. Remember, if chapters 1 and 2 are, there's really no material there. Anything else? Okay, so yes.
Do you have the midterms, the ones that people didn't get, you're absent?
For people that were absent and haven't, yeah, I have them. See me during the break or after class. I have them with me, yes.
After we take the final, how soon are the grades posted and how do we follow?
After you take the final, when will you see your grade? So, you guys are my Tuesday class, so you kind of get the short end of the stick there because I'm only going to make 1 trip to the Scantron machine, and I'm going to do that Friday after my Thursday class has taken their test. So, let's say the following Monday, which is nearly a week for you guys, but they should definitely be posted by that Monday.
Will that be posted on the same Canvas that we go to look at this class?
So this is the first quarter we use Canvas, the my.uclaextension.edu. So I always just send my grades off to Extension, and then they post them somewhere. In the past, they posted them on a different website than our course website. But now that our course website has changed, the answer is I don't know. But I will find out and write it on the board on the day of the final. So I don't know where they post them. I just send them a spreadsheet. Anything else about the exam, grades? Yes?
So will Canvas post like our homework guide as well as the midterm?
No. The only thing I send to them is the final score for the whole class. If you want to know any individual part of it, send me an email. The thing is though, so it's week 11 of a 12-week course. I can tell you all the little secrets. You get free 10% on the homework. I have 232 students this quarter, and I'm 1 person. I don't get TAs or anything. What that means is I don't look at the homework. That's why I post solutions. So everyone in this room, even if you didn't turn it in, you get a full 10% on the homework. It's my idea. It's my version of a curve. It's there to bump up the grades by 10% for everyone. So that's why I don't post your homework score. Don't feel, oh, maybe I got 8% and that's from homework, that's why I missed it. No, you got 10% on the homework. Anything else? With that said, that doesn't mean don't do homework 3. The reason I assign homework, you get out of it what you put into it, right? And if you struggle with it and understand the material, you're going to be grateful you did on the day of the final. Yes?
For 6, 7, and 8, are there going to be, is there going to be terminology on the final in terms of vocabulary, things like that?
So I get that question a lot. Will there be terminology or vocabulary questions? Not specifically, but you need to know, if the question asks you, give me the 95% confidence interval for whatever, if you don't know what the phrase 95% confidence interval means, then you're going to get it wrong. So in that sense, there is terminology. You need to know what I'm asking for, and that means understanding the words we use in this class. So yes, I would say. Anything else about the exam before we start the review? Yes.
Sorry, last question.
Uh-huh.
There's another review on Saturday.
Yeah, so this Saturday, I've sent out an email about it. You all should have seen by now. It's in a different room, so check the email. There is a practice problem day. I don't want to call it a review day, but I guess it is. I'll pass out problems. I'll say do problems 1 and 2 for 10 minutes. Then we'll go over them on the board, just like we do with the practice problems we have in this class. My office hours, I believe I sent an email either today, was it? Maybe yesterday, I don't know.
Yeah, today.
So my office hours have changed for the better. They'll be more convenient. So from now on, they're 5 to 6 p.m. Tuesday, Thursday. That just means really, so if you didn't come today, there's 3 chances left. It's this Thursday, next Tuesday, and that Thursday of next week. Okay, let's get started with our review. Did you have a question?
Yeah, but it's okay.
No, go ahead.
No, it's okay. Yeah.
Great. Yes.
So I don't think this was last week. Where can you go with the practice worksheets that you did in class?
They're under modules on the course website, but they're a little outdated right now. I think I've only posted up to the midterm. I'll make sure to post all 8 of them tonight. Anything else? All right, let's start with our review. Let's go all the way back to chapter 1. When I introduced the class, I said there's 2 types of variables we can look at when we collect data: numerical and categorical. Numerical measures some quantity with numbers. Your height, your weight, your age, these are all numerical variables. How many hours you spend studying or watching TV, numerical variables. A categorical variable is something that can change from one person to another or one object to another object, but is not a number. You're not measuring something, you're measuring the quality of something, your hair color, the car you drive, whether it's Ford or Mercedes. That's a categorical variable, the color of your hair, your gender. Things that people have different values for but are not a number. The names are very descriptive. Numerical is numbers, categorical is categories. We talked about, so probably the most important thing from chapter 1 was when we can draw causal conclusions. I want to be able to say I gave these sick people medicine, and now they're better, and they're better because of the medicine, not just because people get better. So we had 2 kinds of studies. We have experiments and observational studies. In which of these can we conclude a causal relationship?
Experiment.
In an experiment, the reason we cannot conclude a causal relationship in an observational study is confounding variables. Confounding variable is, as the name sounds, it's something that confuses the situation. The example we had was wrinkles and gray hair. We see these happening together. People that have wrinkles are more likely to have gray hair and vice versa. What do we call that?
Association.
An association, when 2 things go hand in hand. But there's some third variable, in fact there could be others, that causes both of these. Age is what causes your wrinkles and what causes gray hair. Age is an example of a confounding variable. On the midterm we had ice cream sales, or on one version of the midterm, and murder rate. This is true in reality, that when the ice cream sales increase in a city, we also see the murder rate increase. And when the murder rate drops, it so happens that ice cream sales also drop. Is this because people love ice cream so much they gotta murder someone? No. Is it because murderers end up with a dry mouth and need ice cream? No. There's a third variable that's causing both of these things. That was temperature. So the midterm temperature was a confounding variable. When it's winter, people are inside, and you typically, I guess, don't kill your own family.
Yeah.
It's when it gets hot and people go outside and the trouble starts and people start murdering each other. I don't need to explain to you why, as the temperature increases, ice cream sales go up. So these move in the same direction. They're strongly associated, but they're not causing each other. and that's due to a confounding variable, temperature, and we cannot conclude the causal relationships. So when can I conclude a causal relationship? It's when I have a properly randomized experiment. The randomization, meaning I take my however many test subjects I have and I randomly put half of them in the treatment group and the other half in the control group. Now on average, these two groups are the same. They have the same average temperature. They have the same average murder rate. They have the same average ice cream consumption. The same percentage of people with gray hair. They have the same everything on average. So if I give one of these groups a medication and not the other group, and then I say, on average, this group improved, then I can say it's entirely due to the medication. It's not due to the more of them got murdered in one group or the temperature was higher, because on average, that was the same in both groups. Questions there? So the key there is then the randomization. So in a properly randomized experiment, we can conclude a causal relationship between treatment and outcome. In an observational study, we never can, because we didn't do anything to account for confounding variables. All right. Then we got into some actual math in chapter 3. Or in chapter 2, we saw some graphs. The histogram. When we visualize distributions with the histogram, remember my y-axis is frequency, or just how often that value occurred. The x-axis would then be the actual values the data takes. So if this were a dice, I'd have 1, 2, 3, 4, 5, 6 on my x-axis. And then if I flip that dice 1,000 times, each of these bars would be, well, I got a 1 this many times, I got a 2 this many times, and so forth. Certainly with a dice, I'd expect them all to come out about the same height. X-axis, data values, y-axis, how often that value occurred. What do we call the tallest bar? Let's say 4 happen to come up a lot more often than all the other values.
Symmetric.
The value itself, 4, the most commonly
Mean.
occurring value. It's not the mean.
No.
It's the mode. The mode is the most commonly occurring value, and if we have a distribution that has 2 peaks like this, that's why we call it bimodal. It has these 2 clusters where a lot of data appear. When do we see these bimodal distributions? So just want to make it more obvious.
When you're talking about 2 separate age groups, like a child and an adult, weight, or whatever.
So more generally, it doesn't have to be age groups. It's just any 2 separate groups that have a different average in whatever quantity I'm measuring. So on the midterm, we talked about universities' tuitions. Or I gave you a distribution like this, and I said which of these situations could create this distribution. I have, so this axis here is tuition, money. I'm going to have 2 groups. What are these 2 groups?
Public and private.
Public and private universities. Public schools, here's their average tuition, and they kind of cluster around here. And then here's the average for private schools, whatever that average is, they kind of cluster around here. Makes sense that private schools have a higher average than public. So that's why we see these 2 groups. All the public schools around here, all the privates around here. So it's anytime we have 2 different groups with a different average. We talked about other shapes of the histogram. When we have a long tail to the right, when compared to the left. Distribution like this, we call right skewed. We name it in the direction of the slow decline. This means that compared to the left side, I have a lot more extreme values here on the right, but they're increasingly infrequent. The more extreme the values get, the more infrequent they are as well. The reverse case where I have some low values compared to the rest of the data, but they're not that frequent. We call left skewed. A lack of skewness, meaning there's no long tail in each direction, we call it a symmetric distribution. So why do I want to decide if my data is skewed or symmetric? The reason is the mean, one of the quantities we use a lot in this class, is affected by skewness. The mean gets pulled in the direction of that skew. So the extreme example we saw in lecture was we had a village where here was 9 people at 0 sheep, and here's one guy, very short bar, at 1,000 sheep. This is a very skewed distribution, right? The mean was 100 sheep per person, obviously misleading. The median was that there were 0 sheep, a much more accurate assessment of what's going on in this town. So the mean is really affected by these skewed distributions. On a right skewed, the mean will be to the right, or greater than, the median. So remember, the mean is just the average, as we've always known it. If I have 5 numbers, I add them all up and divide by 5. The median, we'll do an example shortly, is just the middle value after I've put all the data in order. On the right skewed, the mean goes to the right of the median. I can use this to tell if the distribution is skewed, because on a symmetric, I'd expect them to be about the same value. In the midterm, I said something about the value of homes. I said that the average house price in LA is $1.25 million. The median house price I wrote as 500-something thousand. The mean was higher, therefore the distribution was right skewed. The opposite is true. If the mean is less, then the distribution is left skewed. So forgive me for stopping to read my cheat sheet. I don't remember everything we covered. So when you might want to have this on your cheat sheet. You may already from the midterm. Remember, spread is also called variability. So because of what I just said about skewness, our measure of center for skewed data is then the median, because it's not affected by the skewness the way the mean is. For symmetric data, they should be about the same, so it doesn't really matter which one we work with. The mean is much easier to work with mathematically. I know we don't like formulas, but having a formula, like add them up and divide by the sample size, is much easier to work with than put them in order and find the middle one, actually. We also had 2 measures of spread, which is talking about how spread out the data is. Distribution that looks like this, that's unimodal and symmetric, is less spread out than one that looks like this, right? And we actually want to measure that spread. So the one we've used, what's the one we've used most commonly in this class? We've been using it a lot.
Standard deviation.
The standard deviation. The formula for standard deviation, I won't ask you to compute it, is the sum of all the squared deviations from the mean divided by n minus 1. We call that SD, the standard deviation. It uses the sample mean in its formula, so then like the sample mean, it is susceptible to extreme values, to skewness. For skewed data, what's our measure of spread? Something that's robust to extreme values. Does anyone remember? The IQR. These go hand in hand. The mean and standard deviation go hand in hand. Remember, for both of these, you need to put the data in order first. So let's do an example of that now. I'll write it out of order since that's how you'll see it on the exam. So if I ask you to find the median, and I know it seems like I'm beating a dead horse, but I see this a lot on exams. People see it written here, they go, oh, the median, because it's in the middle. You're almost right, but you gotta put it in order first. So I have 8, 17, 51, 57, 64, 72, 86. Now it's in order. I have 7 values. The middle out of 7 values is the 4th one. So my median is 57. The IQR, our measure of spread, is Q3 minus Q1. Q3, think of it as the median of the top half. It's the middle value of everything that's above the median. So I ignore the median. I have 3 numbers. The middle one is 72, so that's Q3. The middle of everything below the median, in this case 17, is Q1. 72 minus 17, 55. So I'll have an IQR of 55. Yes.
Are you going to make them 3 on each side?
Yes.
Yeah.
So I think the question is, what if I only had 3 numbers here? Then the middle doesn't exist, so I'd have to take the average of these. On the test, I will make it 7 values. So we don't get into that confusion of what if there's no in between. The answer is you take the average, but I won't put that. The empirical rule was the other thing we learned in chapter 3. The empirical rule is now obsolete. We will use our z-table, which will be included with the exam. You do not need to bring your own. In fact, if you do bring your own, it'll count as a cheat sheet, so don't bring your own. But this has completely replaced the empirical rule. It will not be on there. The same type of questions will be on there, but you'll use them the way we did. You'll answer them the way we did in chapter 6, using the z-table. Questions on here? Chapter 3? Okay. So after we learned all about mean and standard deviation, we made extensive use of it in this course. Our first application of mean and standard deviation was linear regression, which is probably the most common descriptive method. When you hear about people using math to try and predict the stock market or really predict anything that could be predicted using numbers, which is a whole lot of things, it's all based off this method here, linear regression. So there we introduced the scatter plot, which is just the XY coordinate system. In other classes, you've seen it as the Cartesian coordinate system. All our data then appears as points here. Every point has an X value and a Y value. I don't know what your math background is, but what we learn here generalizes. Imagine if I could draw in 3 dimensions and have a Z-axis coming out from the board. I could just as easily fit a line going through all these 3-dimensional points. This being intro stats, we limit ourselves to just 2 variables, X and Y. But try and imagine this in higher dimensions as well. It can be done in dimensions that we can't even imagine, like 10 dimensions. You can't visualize that, you can't draw it. But you can still do regression on it. So, aside from the mean and standard deviation that we learned in chapter 3, we introduced a new statistic here called the correlation. And the correlation, which we denote by lowercase r, measures the strength of the relationship in the data. So if my data is tightly packed like this, it's going to have a high, because this is called positive relationship. As x increases, y in general is increasing. So that'll be a high positive correlation, maybe close to +1, something like 0.6, 0.8. On the other end, a correlation of -1 would be a similar thing, but the data is decreasing. In between, at r equals 0, is where we see no relationship. Here, as x increases, y is still just too unpredictable. In other words, the data is just a random cloud. You really can't get much information out of it. So let's say this here is a correlation of 0.8. If the cloud's actually less packed together, a little more spread out. So this would have been like negative 0.8. Now it might be negative 0.5. Not quite as packed together, not quite as strong of a correlation. Questions about the correlation? It's measuring the strength of the linear association in the data. The more tightly packed, the higher the absolute value of the correlation. The sign is telling me the direction. Does y increase or decrease as x increases? So let's look at an example. So first off, what is my goal with linear regression? So let's say I have this positive association. I see some relationship between x and y, and my goal is to actually find the exact structure of that relationship with the equation of a line. I want to find the line that best fits this data, so then I can say, okay, for this value of x, I predict y is this. For this value of x, I predict y is this, and so forth. So let's actually look at an example. Let's go back to height as our x variable. And on the exam, I will tell you which variable is x and which variable is y. The y variable is the one we're predicting, the x variable is the one we're predicting from. And let's say arm span. I use height a lot because it's well correlated with other physical dimensions of your own body. Clearly, the taller you are, the wider your arm span, being this length here, you're going to have. You need to be given the mean of both, the standard deviation of both, and the correlation between the two. So let's say arm span has a mean of 64 inches. I'm sorry, height has a mean of 64 inches with a standard deviation of 3.5 inches. This is made up data. Don't use this and go say, oh my God, I'm 5 standard deviations above the mean, I'm a giant. Arm span, again, made up data. This may not even come out to a reasonable looking human average as I have it. Is a mean of 160 centimeters with a standard deviation of 8 centimeters. And what else do I need? The correlation between them. This describes just height. This describes just arm span. Correlation is what describes their relationship. Let's say it's 0.95. We would expect that your height and your arm span are highly correlated. Our goal then is to find the equation of the line that best fits through there. That equation will have the form y, which we put the little hat on to mean predicted. But it's predicted y equals a plus bx, where a is my intercept and b is my slope. You can see how with those two quantities I can create any possible line. The intercept is the height of the line, the slope gives me the angle. So if I can move it up and down and then adjust it, that covers all possible lines, right? Our first goal is to find the slope. We use the slope in the formula for intercept, so we always find the slope first. Slope equals the correlation, so you'll definitely want this on your cheat sheet, times the standard deviation of the y variable, divided by the standard deviation of the x variable. So for the example we have, that'd be 0.95 times the standard deviation of arm span, which is 8 centimeters, divided by the standard deviation of 3.5 for height, we get a slope of 2.17. We'll talk about the slope in a minute when we put it in the actual equation. Then we have our intercept. Our formula for intercept is y bar, the average of the y variable, minus b times x bar. Y bar is given as 160 minus b. B is what we just computed, 2.17, times x bar, the average of x's is 64. Your calculator most likely knows this already, but make sure you multiply these first and then subtract whatever that total is from this value here. We get 21.12. Once we have those two quantities, we can plug it back into our actual equation. So I have predicted y, which in my case is arm span, so I'm going to put predicted arm span, equals A, my intercept, 21.12, plus, here it's a plus because I have a positive slope, 2.17, times x. We can put the actual word, height. So this here is the linear regression model or best fitting line for the relationship between height and arm span. It allows me to predict arm span from height. Questions on finding that line? Okay. So once we have it, what do we do with it? Well, we make predictions. So let's say, well, sorry, let's take a step back. Let's interpret the slope and intercept. What is the slope telling me?
The angle.
It's the angle of the line. Remember from high school, rise over run? If I know the run, it'll tell me the rise, right? So a 1 unit increase in x, let me erase all these dots so it's less messy. Here's my line from using that equation there. Here's x1 and here's x2. Let's say this change from the first x to the second x is exactly 1 inch. That means that the corresponding change in arm span, this distance here, would be 2.17. It's a unit increase in x, meaning a change of 1, whatever unit that is associated with a slope increase in y. So the slope is giving me the rate of change of y as x changes. Had x increased by 2 instead of 1, then y would increase by 2 times the slope, 4.34. So it's the rate of change of y as x changes. Yes?
And if we had a negative number, that means it would go down.
If you had a negative slope, it's the exact opposite situation. Here's my change in x. My change in y, obviously, is negative now. It'd be a drop of 2.17. Obviously, here I'm talking this direction. Still saying this, same direction. Positive 1 inch increase would be a drop of 2.17 if we had a negative slope. So in no practice problem this quarter have I given you a negative slope. And the reason is I want you to understand what's going on here. Negative doesn't change the situation anything at all. I just do positive so that it's always the same and you don't get confused by the negative versus positive because there's no real difference there. I want you to understand the concept, not get confused in the calculation. So on the test it'll be the same. It'll be a positive slope. That's just for consistency. What about the intercept? So the slope is the rate of change of y as x changes. What is this intercept here? The intercept is just the predicted value of y when x equals 0. So this is a big if for x. Sometimes x just can't be 0, right? If I'm talking height here, a height of 0 makes no sense. So sometimes the intercept has no real world meaning. Sometimes it does. On the test, I'm not going to put the type of question, does it have a real world interpretation or not? Sometimes it can be just vague and ambiguous, so that won't be on there. But you should definitely know what the slope means, the rate of change of y as x changes. Okay, so let's make a prediction then. I want to use this line to predict the arm span of someone with a height of 66 inches. The way you make a prediction, just plug it in for that variable. So a height of 66 inches. I have 21.12 plus 2.17 times 66. I get 164.34. That'd be centimeters because that's my unit for arm span. Yes. Yeah, I can make a prediction as long as it's not extrapolation. Remember, extrapolation is when I make a prediction for an x value that's outside of the range of the x data that I actually have. But yeah, any number in that allowable range, you just plug it in. So this is my predicted arm span of someone who's 66 inches tall, exactly. What if I go out into the real world and I find an actual 66-inch tall person, and their actual arm span is 170 centimeters? We define the residual as the actual value minus what we predicted. So the residual for this individual,
Outliers.
actual minus predicted, (170 minus 164.34). I'm obviously going to get a positive value there. What is that exactly? Positive 5.66. A positive residual always indicates that I've underestimated. It was a little bit lower than what it should have been. And the inverse is true. A negative residual means the model has overestimated. That's just a consequence of the fact that it's always actual minus predicted. Questions there? Okay. So the last thing I want to talk about in chapter 4 then is this quantity r squared, the coefficient of determination. We compute it by just squaring the correlation. So in our example, we had a correlation of 0.95. 0.95 squared is 0.9025. Just for the sake of simplicity, I'm going to call that 90%. 90% what? What does the r squared, the coefficient of determination, tell me?
Correlation.
It's not the correlation.
For
That's
every
what.
difference, there's
Sorry.
for the difference in R, there's a 90%.
So this.
Y is explained by X.
Yes, it's the percent of the variability in y. So if I have no height information, I just have a bunch of arm spans. I go, okay, well, there's people with short arm span like a T-Rex, and then there's people with wide arm spans. And let's say I'm a naive person, I've never seen a human. I go, why is that? That some people have such variety in arm spans. Then I look at the height data, and I see this relationship. I find the best fitting line with a positive correlation, a positive slope. I go, oh, okay. Well, it's because as people get taller, their arm span tends to increase. So there may be a lot of factors that go into a person's arm span. Certainly there's variety even within people of the same height. I could find a lot of guys that are the same height as Michael Phelps that don't have his arm span. But certainly height is one of the factors that go into determining your arm span. And that's what r squared is telling me. What percent of this total variability, you could think of it as just what percent of the total standard deviation of arm span is actually explained by the x variable that I chose. So in this case, 90% of the story of arm span can be explained by height. And in general, r squared percent of the variability in y can be explained by x. Obviously, the higher, the better. The closer this is to 100%, the better your model is at actually predicting y. So if this had like a 20% R squared, that may not be so good for predicting the stock market. If I had a 99% R squared, I'd be a billionaire, right? We've never gotten close to 99% R squared, unfortunately. Questions there? Okay, so that's pretty much it for linear regression. That was chapter 4. Make sure you have these formulas on your cheat sheet. There's no limit to what can be on the cheat sheet, so feel free to put solved examples even that you got from the midterm or that I'm doing now. If it reminds you how to do it, that's fine. That's a good thing. So then we looked at chapter 5, which, so I don't actually have total control over this class. We do follow the standard UCLA curriculum, which I had no say in. I do believe chapter 5 is somewhat oddly placed, just kind of thrown in there. So while chapter 5 is probability, I want to remind you everything we do in this class is probability. Probability is not just limited to chapter 5. In chapter 6, when I give you IQ, mean and standard deviation, and I ask you the probability an IQ is above 120, that's probability, even though it's not in chapter 5. What chapter 5 really is kind of a step back. It's these general rules that apply to all probability situations. Maybe the best example is that we learn the complement rule in chapter 5, and that complement rule is true for anything, yet we really made use of it a lot in chapter 6, right? Remember, anytime I have probability z greater than something, I need to do 1 minus the probability that z is less than that same value. That's an application of complement rule. So probability is not limited to chapter 5. Another way to say it is these rules are independent of how we compute the probability itself. These rules are about how we combine those probabilities into sequences of events. So let's just get started with some examples. The first thing to know, and the most obvious, is a probability goes from 0% to 100%, or in decimal from 0 to 1. Any negative values, anything above 1, you've made a mistake. It's not a probability. We started with the addition rule. So a lot of these questions, and we'll see examples, boil down to, are you combining events using the word or are you combining events using the word and? The addition rule is the or rule. It tells me that the probability that A occurs or B occurs, this is what's called inclusive or, meaning this is A occurs or B occurs or they both occur. That'd be just fine, if they can both occur. This equals the probability of A by itself plus the probability of B by itself. But in doing so, I've double counted the A and B. So think of, in class, I had a certain percentage of people speak French, a certain percentage of people speak Spanish. Some people are trilingual and speak both French and Spanish. So if I just count all the French people plus all the Spanish people, then I've double counted all the people that speak both, right? So that's why I need to subtract that off once, minus the probability of A and B. Sometimes this can't even happen. Sometimes this is just 0. The probability A and B equals 0. What do we call this situation? Not independent.
Disjoint.
Disjoint. We say that A and B are disjoint. And the normal everyday way of saying this would just be that A and B are impossible. It's impossible that they occur together. They're mutually exclusive.
Can you give an example of a disjoint event again?
Yes, disjoint would be passing and failing this class. What's the probability you pass and fail this class? 0. Cannot happen. What's the probability that I get heads and tails? 0. The probability that it rains and
Sunshine.
we have a drought, 0. Can't have both. Just any two things are impossible. Getting 5 of a kind when you're playing cards, impossible. I could go on forever with impossible. Speaking of poker, yes.
Sorry. Earlier, as we spoke about the tables, using the tables, we still could use them, but you don't recommend using this rule in the table probabilities.
So, as I said with the midterm, if I give you the data in a table, the two-way table, which we'll see an example of, you don't need necessarily to use these rules. You can, if you forget how to read the table, but you don't need to. There's a quicker way, but we'll talk about that when we get to the tables. If I give you the information just in a paragraph, like I did in the lecture slides, you have to use these formulas. So an example, what's the probability that I draw one card from a deck of cards and it's an ace or a black card? Are these disjoint events?
No.
No,
No, why not?
because they could happen at the same time.
Because it can happen. There's in fact 2 of them in the deck, the ace of spades and the ace of clubs. So it's this probability of an ace plus probability of a black card minus, they're not disjoint, so I do need to subtract that non-zero probability, the probability of ace and black. What's the probability of an ace in a deck of cards?
4 out of 52.
4 out of 52. The probability a card is black in a deck of cards?
26 out of 52.
26 out of 52.
-2.
Minus, there's 2 black aces in the deck. Minus 2 out of 52. Again, this illustrates why I need to subtract, we call this the intersection. Because when I counted up the aces and the black cards, these 26 plus this 4, they each included the 2 black aces. They got double counted. So I need to subtract the 2 black aces. So I get 28 out of 52. What about on a dice, the probability I roll 1 or 4? Let's make it a little more interesting. Roll greater than 5 or less than 3. Okay, so or we can start with the addition rule. Have the probability of greater than 5 plus the probability of less than 3 minus the probability of greater than 5 and less than 3. Let's start here. Are these disjoint events?
Yes.
It means cannot happen. Can you think of any number that's greater than 5 and less than 3 at the same time? No. Doesn't exist. This equals 0. These two events are disjoint. What's the probability of greater than 5 on a dice?
1.
1.
6.
That's just the number 6. So here, unlike the normal, it does matter whether it's greater than or equal to. Had I put or equal to, it'd be 2, right? That's 1/6. How many numbers on the dice are less than 3?
2.
The 1 and the 2, so that's 2 options out of 6. So that's a 50% chance that I roll the dice and I get something greater than 5 or less than 3. Questions there? So then let's look at the AND rule, the multiplication rule. So first let's define independence. The formula, which we'll make use of soon, probability of A given B equals probability of A. That's our definition of A and B being independent. for any problems, so the same thing was true on the midterm. We had the general multiplication rule, which I'll write here, but I'm about to cross it out. That's the probability of A and B equals the probability of A given B times the probability of B. This is to account for any dependency of A on B. I'm not going to ask this sort of thing on the final in the same way that I didn't ask it on the midterm. The reason being that the vast majority of the time that the multiplication rule is useful, it's for independent events. So assuming A and B are independent, the probability of A and B equals probability of A times probability of B. And this extends infinitely. Most of the time in this class we use it with a lot more things. If I have A and B and C and D, then this is, it goes on forever. And we usually use it in a larger sense. I say, what's the probability that I get all heads out of 5 tosses? Well, it'd be 0.5 times 0.5 times 0.5 times 0.5 times 0.5. So let's look at that. Let me first do the independence example because my next example kind of goes over into chapter 6. So I could ask the independence example the way I did in the lecture notes. Go back and review the Spanish, French, are they independent example from the notes. But on the final, much like the midterm, the independence question will come from table data.
And what really independent means is if it affects one another.
Yes, does it have any effect on the probability that the other thing occurs? If the answer is no, they're independent. So let's talk about legalizing marijuana, a subject that comes up every time we vote. And gender. And let's say I have, do you approve of marijuana legalization in California? Yes, no. Gender, male, female. So again, the way this table reads is I have 10 males who do not support marijuana legalization and so forth. And the question is, are gender and opinion, this would be your opinion on marijuana's legal status, independent? And again, I commonly get the question, well, no, they aren't, because my gender has nothing to do with my opinions on social issues. And that's fine. This is not a philosophical question. It's a question of detecting trends. Do we, on average, see women and men having different opinions on this? And we answer that using our definition of independence. It does not matter. So I have A and B. I need to pick one for each of these, A and B. It does not matter which one I pick as long as the other one comes from the other side of the table. So we want to follow this pattern, probability of A given B. Does that equal the probability of A? So let's choose something for A. What is A?
Male.
A can be any of these things. I heard male. So male given something, does it equal the probability of male? Now the only restriction on B is that it comes from the other side of the table. We chose male from the gender side, so now I need to pick yes or no.
Yes.
Yes. Doesn't matter which. So it's the probability that I'm a male, given that I am in favor of legalization. If that equals the probability that I'm a male, without any consideration to my opinions on legalization, then clearly my opinion has nothing to do with whether I'm a male. Or in other words, knowing this does not change the probability that I'm a male. That would be independence. So given that I support legalization, I'm going to limit myself then to just these 15 people that support legalization. Of those 15, how many are male?
5.
5. Which is 1/3. Now let's look at probability of male overall. How many males are here?
15.
15 total males. Out of how many people?
20, 25, 30, I mean 45.
45. 15 out of 45 in your calculator, you'll get 0.3333. Also 1/3. They're the same, aren't they?
Yeah.
So that means that your opinion and your gender are independent. Or in other words, men and women favor and oppose legalization at the same rate. Therefore, knowing whether or not a person favors or opposes legalization doesn't help you guess their gender at all, and vice versa. Questions? Okay. Let's talk about the law of large numbers.
And we had a conceptual problem for this too, right?
I'm sorry?
On the midterm, we had a
On the
conceptual
midterm,
problem.
we had a conceptual question regarding the law of large numbers. So, the law of large numbers, it can be a bit of a mouthful to try and state it, but it's a simple idea. Let's say I have a coin that is exactly, for sure, a 50-50 coin. And I flip it 5 times and I get 3 heads, 2 tails, 60-40 split. That's not so strange. In fact, there was no way I was going to get a 50-50 because it was only 5 tosses, right? If I flip it just a few number of times, I can get any ratio. It's not that unusual, even though I expect 50-50. If I flip it 1,000,000 times, I'm virtually guaranteed to get something really, really, really close to that 50-50 split that I expected. So to graph it, on this axis, I have the percent of all tosses that are heads. And on this axis, I have n, the number of times I flip the coin. The law of large numbers is saying that if, when n is still low, this could fluctuate towards all sorts of weird things. But as n gets larger and larger, I'm virtually guaranteed, so right here is 0.5. I'm going to converge to what it should be. Another way of looking at it, which is what was on the midterm, was, so then let's say I have flipped a coin an unknown number of times, and I got really strange results. 70% heads, 30% tails. Do you think I flipped it very few times or a lot of times?
Few times.
Very few. So strange results are more likely with only a few tosses. Questions there? Okay. So now let's talk about, let's do an example with this multiplication rule. Let's say the probability, and we're going to use this for a few examples now, that a dog has rabies, this is just, let's say for any given dog in the world, is 20% chance. Obviously a made up number, but it works here. If I work out a pound, what's the probability that the next 3 dogs, that I get a rabid one, so the next one is rabid, the one after that is also rabid, and the third one after that is not rabid. That's rabies complement. So what's the probability of this occurring? Well, it's an and question. This means the first dog is rabid, and the second one is rabid, and the third one is not. So by multiplication rule, it's just the probability of rabid, 0.2, times the probability of rabid, 0.2, times the probability of not rabid, which would be what?
0.
0.8. If the probability of rabid is 20, then not rabid is 80.
Oh.
Straightforward application of multiplication rule. The same would be true if I gave you heads, tails, heads. You do 0.5 times 0.5 times 0.5. This comes out to 0.032. What if instead I asked you, what is the probability that out of the next 10 dogs, at least one has rabies? At least one of next 10 dogs. So what does this at least one tell us to do?
Complement.
For argument's sake, I'm going to change this 10 to a 5. That's complement rule. Why do we want to use the complement rule? Well, the sample space of the number of dogs out of the next 5 that could have rabies is anywhere from 0 to 5. At least one would be all these. So it's true, this is an addition rule problem. At least one would be 1 has rabies, or 2 have rabies, or 3 have rabies, or 4, or 5. And I could find these 5 probabilities and add them up. But that's the long way. Instead, I want to just rewrite, as we did in the notes, the sample space as 0, and I'll call this whole thing at least 1. Well, I know the probability of 0 plus the probability of at least 1. What does that add up to? 1. That's all possible outcomes, so it has to add up to 1. In the same way that the probability of heads plus the probability of tails adds up to 1. So this statement here is true. Bring it up here. So much like if I have A plus B equals 1, that means that B equals 1 minus A. Just algebra, I subtracted A from both sides. That's all the complement rule is. If I want the probability of at least 1, I see that it equals, just by rearranging it, 1 minus the probability of none. So it's allowing me to find the answer I'm looking for, which is the sum of these 5 individual probabilities, by only computing this one probability. So that equals 1 minus, we still have to find this, what's the probability that none of the dogs are rabid? Is that an or an and problem? Start listing the dogs. The first dog is not rabid, and the second dog is not rabid, and the third, and the fourth, and the fifth. That's what it means for none of them to be rabid. So I have 0.8 to the fifth. 1 minus 0.8 to the fifth. Much easier to do 1 minus 0.8 to the fifth than to find all of these, which, now that you've seen binomial in chapter 6, you know is not that pleasant. Questions there? Yes.
Are we allowed to use the binomial table?
So are you allowed to use the binomial table on an exam? The answer is yes. You can bring one because it'll count as one of your cheat sheets. I don't recommend the binomial table. You don't need it. The true utility of the binomial table is if I give you binomial questions that say 3 or more, forcing you to find multiple binomials. Then the binomial table is useful. I don't do that, and I'm not going to do that. So there's really no use in the binomial table. You can bring it, but it'll count as a page of cheat sheet.
2 pages, yeah.
You can have 2 pages, 4 total sides. Okay, then let's get into chapter 6.
What was the binomial table?
I'm sorry?
What was the
The
binomial?
binomial table is something I don't teach in this class. So she learned it online or somewhere else. If you want to go look it up and you think it'll helpful, bring one. You don't need it. Also, the binomial table is only useful for the specific values of p, which it's unlikely I'm going to accidentally ask one of those exact values that's on the table. So don't break it. Wouldn't help that much. So at 7:35, let's take our 10-minute break. Let's meet back here at 7:45, and then we'll start chapter 6.
Done by 8:30.
I'm guessing not. We are covering the whole class in one day. Before 9, somewhere between, probably around 8:45, somewhere around there. Was my guess.
Do you know if this laptop hits pause?
I don't know.
I'm afraid to hit that button right now.
Oh, yeah. Oh,
Yeah, I'm afraid to hit
just
the
let
button.
it.
Yeah,
Should probably add it.
probably.
So we're gonna add my first one and then. That's maybe it's, the house that you how much of it had.
I was like, some shit happened, man. I was like, cause he's like, oh, we're going over to chapter 6.
I was like, I was gonna hit that button.